Now that we have an idea of what a partial derivative is, I would like to talk about how to actually interpret what the partial derivative is telling us with a couple of examples. We know from Calc 1 that a derivative represents an instantaneous rate of change, or the measurement of the rate of change of a variable as another variable changes. That interpretation will still hold true to partial derivatives, but because we have multiple variables, it'll be necessary to treat other variables as a constant as we're analyzing certain partial derivatives. In this example, C represents our dependent variable, and this is the cost of a pizza. My background before I was a professor of mathematics was working as a pizza guy, so expect a lot of pizza-related examples. Now, with that in mind, when you are ordering a pizza, it is typically a function of two things: how much this will cost. S is going to represent the size of the pizza. Generally, size of a pizza is given as one measurement, the diameter of a round pizza, for example. And T will represent the number of toppings. Now, there are situations where you can talk about premium toppings like chicken or steak or feta cheese or artichoke hearts or good stuff like that. We'll just assume that that counts as multiple toppings. So if I wanted to interpret some partial derivatives, so first off, the notation that we would use for these. Two possible notations to represent the partial derivative of the cost function with respect to the size of the pizza. We can either do dc over ds, or we can state the original function with a subscript s after this. So the interpretation of this would be, at what rate does the cost of the pizza change as the size of the pizza changes? Now, generally speaking, when we order a larger pizza, it's going to cost us more money, so we would interpret this as an increasing function with regard to the size of the pizza. So in either case, we could interpret this to be positive. If you order a larger pizza, it will cost more money. Now, this is assuming that you are keeping the number of toppings consistent. So we wouldn't be comparing, say, a medium 3-topping pizza with a large 1-topping pizza. It would be like comparing a medium 1-topping pizza with a large 1-topping pizza. So generally speaking, when you're keeping the toppings consistent, it will cost more to get a larger pizza. Now, on the other side of things, we could also talk about dc over dt, the partial derivative of the cost of the pizza with respect to the number of toppings. So this is saying if we keep the size of the pizza consistent and order more toppings, generally what happens to the cost of the pizza? This would be another situation where we can expect this to be an increasing quantity, so this derivative would be greater than 0. So the interpretation would be, if you order more toppings, it will cost more money, which I think is pretty reasonable. You order more toppings, it's going to cost more money. Now for another interpretation. In this one, we're going to have that A is a function of T and W. A is going to be referred to as the apparent temperature. Up here in Michigan, we enjoy all sorts of inclement weather. I remember that earlier this summer it was 63 degrees out with a freeze warning, so the temperature was just going to vary that much. So apparent temperature is not what is the actual temperature, it's how does it feel outside. So a phrase that you'll hear a lot in a Michigan summer is, well, it's 80 degrees outside, but it feels like 87. T is going to represent the actual temperature, and W is going to be the wind speed. Now, this applies especially in Michigan winters. We say, it wouldn't be so bad if it weren't for all the wind chill. So the more wind there is, it typically has a pretty drastic effect on the apparent temperature. So let us assume for a moment that we wanted to talk about the partial derivative of the apparent temperature with respect to the actual temperature. Or this would be the notation that we would use for the other partial derivative. That's f with a subscript t of t and w. So this is saying, assuming that the wind speed stays consistent, if the actual temperature outside changes, how does that have an impact on the apparent temperature? So if it's 30 degrees outside versus being 40 degrees outside and the wind is staying consistent, what's going to happen to the to the apparent temperature? Well, in this case, that would be an increasing function as well. If the actual temperature outside increases, then we would expect the apparent temperature to increase as well. So if the actual temperature changes, we'll say specifically if it increases, the apparent temperature, apparent temperature increases as well. Now for an example of something that is not consistent with what we've seen so far, the partial derivative of the apparent temperature with respect to the wind speed. So let's assume that it's a nice balmy 20 degrees Fahrenheit outside during a Michigan winter, and your two options are you're allowed to have a 5 mile per hour wind or a 20 mile per hour wind. As the wind speed increases, what is going to happen to that apparent temperature? Well, as the wind speed increases, we are going to feel a decrease in the apparent temperature. The more airflow there is, typically the colder it feels. So we'll say if the wind speed increases, the apparent temperature, how it actually feels outside, decreases. So as one quantity gets bigger, the apparent temperature gets bigger, and as the other quantity gets bigger, the apparent temperature gets smaller. So interesting phenomenon there.